We build our physics on top of our intuitions, and the intuition for a very long time, as represented in Newtonian physics, is that time is a river that flows past, and we passively track that. And then with Einsteinian physics, the idea was, okay, well actually it can stretch or squish depending on your frame of reference. But I think it's a lot worse than that, and that's what I'm going to tell you about very briefly. It appears that there's actually a neural relativity. It appears that time ain't what you think it is. And I've been studying this for many years, but I'm just going to dip into 4 examples that I think illustrate these points pretty well. So the first one I'll show you is a very simple visual illusion that I started looking at a while ago. It's called the flash lag effect. If you have a moving object, let's say in this case a ring moving to the right, and you flash something right in the middle while it's moving, that's what actually hits your retina on the top, but what you perceive is that the ring was ahead of the flash. I'll show you demo this in a moment. But the question is, why does this happen? So what had been proposed in the literature is that maybe what's happening is you're collecting up information in time, the flash happens, and then your system guesses forward. It says, well, where is the moving object likely to be? In other words, there's motion extrapolation. The idea is that when you have moving objects in the world, by the time the light strikes your retina and you process the information, the moving object has moved on, so maybe what the brain's doing is guessing ahead. So let me show you what this looks like. This is the flash lag effect. I have a ring going around in a circle, and let's see if I can do this again. And you can, let's say you're fixing on that red square there. You can see that even though the flash is occurring right in the middle of the ring, it doesn't look like it. It looks like the ring is ahead of the flash. Does everyone see that? Okay, that's the flash lag effect. Okay, I had reasons to doubt this extrapolation framework, which is that the brain is guessing ahead. So I did a very simple experiment, which is I have a ring come around and a flash happens just like you saw, and then one of 3 things happens at random. Either the moving ring keeps going like you just saw, or I have the ring stop, or I have the ring reverse direction. So the key thing to note here is that everything up to and including the flash is identical, and all I'm doing is I'm changing what happens in the future of the flash. Okay, so if extrapolation were happening, you would of course expect to see the same thing every time, which is that the ring looks like it's ahead of the flash, because it shouldn't matter what happens after the flash is already gone. Well, here are the 3 conditions very rapidly. There's continuous, there's reversed, and there's stopped. So let me show you this again. Here's continuous, reversed, and stopped. So what did you see here? It looks like in the continuous case, it looks like the ring was actually below. In the reverse case, it looks like the ring was above, right? And in the stopped case, it looked like they were aligned. Did everyone see that? Okay, so if I quantify this is sort of the only graph I'll show, but so here's the continuous, the stop, the reversed case. Here's a measure of the perceived displacement. We use typical psychometric studies to quantify this, where we sit people down in front of computers, we manipulate where the ring and the flash are taking place, they answer over hundreds of trials how they're arranged, and we can quantify exactly that displacement. So the symbols represent different subjects here, but the key is, you see that in the continuous case, subjects perceive the ring about 5 degrees past the flash. In the stopped case, there's no illusion at all, and in the reversed case, they perceive the ring above the flash, just like you saw. Okay, well, why is that so weird? It's so weird because I'm asking people what they see at the moment of the flash, and their answer depends on what happens in the future of the flash. And remember, these conditions are randomly interleaved. So there's only 2 possibilities here. Either our subjects are clairvoyant, which you don't think is happening, or the perception that we attribute to some moment in time actually depends on what happens next, in a little window just after the event. Okay, so it's not that extrapolation is occurring. That's not what's happening. Instead, it's something more like interpolation, where after the event, the flash here, your brain continues to collect up information, and it retrospectively says what it thinks it saw. Now, obviously, there's nothing backwards going on in time, so probably the right way to look at this is here's time in the outside world, whatever we mean by that, and there's the flash, and then you have time inside your head. And of course, we know that it takes a while when there's a flash in order to actually perceive that. But what this very simple experiment shows is that there's a window of time after the flash that all gets subsumed into what you believe you saw at the moment of the event. Now, I'm not going to show you the details, but I did a lot of experiments to quantify that window. It's about 80 milliseconds, and this is related to what people sometimes refer to as the specious present, although we can come back to this point. But this is about 80 milliseconds here of information in the future of an event influences what you believe you saw at the time of the event. So I'm skipping over all the detail stuff. I just want to give you a flavor of this. Surprise number one is that you live in the past. Okay, and I don't mean like this. I mean that when you think the moment now occurs, it's already happened, right? It takes neural signals are shockingly slow. They move around the brain. Some neural signals are moving at 1 meter per second. Think of how slow that is compared to the speed of electricity. Okay, so things are moving around very slowly, and what you have in the brain is this vast neural real estate, and you have signals coming in. They have to move around, they have to get stitched together, and your brain has to put together a story of what's happening in the outside world. And by the time it's done that, the moment now is already gone. I might be done with this talk for all you know. So what this means is that your perception is like one of these live television shows, which is not actually live, right? These live television shows they're aired with a little bit of a delay in case somebody cusses or falls down. That's exactly what's going on with our perception. It takes time to put everything together, so we're living with a little bit of a delay. Now, the experiment I just showed you has to do with vision and collecting of visual information. I've been suspecting for a while that probably what the brain does is it waits for the slowest signals to arrive before you have a perception. So it turns out that if I touch your toe and your nose at the same time, you will feel those as simultaneous. Well, that's really weird, right? Because the signals from your nose reach your brain essentially right away. The signals from your toe have to climb all the way up your spinal cord to get there. So when your brain receives the signals from your nose, does it say, okay, I'm not going to perceive anything until I see what else is coming up the pipeline? Essentially, yes. Essentially, that's what happens. And actually, a couple of years ago, I was the hero of short people for about a day because I announced on NPR that this made me think that tall people probably live further in the past than short people, because tall people have to wait for the signals all the way to come from their farthest appendage before they can actually perceive what's going on. That means people closer to the ground are closer to the border of the present. Okay. So this is what I showed you with this very simple visual illusion. And then what I've been doing for a while is really trying to understand the relationship between these two lines, between time in the outside world, whatever we mean by that, and subjective time. So for example, can there be time warping? Can you perceive something is happening faster or slower than it's actually happening in the outside world? And what about gaps in time? We have gaps in time all of the time. So think about whenever you blink your eyes, the world goes dark for about 80 milliseconds. It's black. And you don't notice that at all. You don't notice that gap in time there. Now, if I came in and I flicked the lights on and off, you would notice that immediately, right? That would be easily noticeable. It's because it's a self-generated movement. We have this gap in time. It doesn't seem to concern us. It turns out it's a lot worse than blinks, because every time you move your eyes in a ballistic movement called a saccade, you make these all the time, and it turns out most of your visual system shuts down during a saccade so that it doesn't look like the world is screaming past. And you don't care about those gaps in time either. So somehow your brain takes care of these gaps and stitches things together. So this is the stuff I've been studying, and I'll just give you an overview of of 3 more surprises in the last decade that I've come across about time. Okay, and one of them that I want to mention is what happens when you get your motor systems involved, what that does to time. So that's what I'll tell you about now. But in order to do that, I'm going to step back in history just a bit to tell you about Kublai Khan, who was the emperor of the Mongols, and he controlled, by the time he was an adult, the largest empire in history at that time. So this was what he controlled, and he positioned himself over here. And remember, this was in the days before cell phones or internet or Morse code. So the question is, how did Kublai Khan know his empire? Right? It was way too vast for him to have any sense of what his empire was. So what he did is he would hire emissaries, like Marco Polo, for example, and they would travel to the distant reaches of his empire, and they would convey news back to him so that he could know what he controlled. Now, of course, it was more than just one. He had multiple emissaries. that would go and explore his empire and come back and tell him news. Now, I've never heard any historian address this, but I imagine this must be true, that Kublai Khan had a temporal problem, which is you might get one emissary coming back and telling you about a war that has just ended, and another one coming back and telling you about a war that has just begun, and they're actually talking about the same war, but because of weather and travel problems and so on, you might get these guys streaming in at very different times. And his challenge is to figure out what actually happened in his empire temporally, given that these guys are getting there at different rates. So you see Kublai Khan's problem. It's exactly the problem that the brain has. So when the brain puts out a motor act, like sends a motor act down, kicking the ball, it gets all these sensory signals back. You have vision, you have touch, you have hearing the ball. And the problem is that all of these things are not only processed in different parts of the brain, but they're processed at totally different speeds. It turns out that all your different senses have completely different architectures for processing. Your sight and your hearing and your touch have different architectures, and they process at totally different speeds. Okay, so in this vast neural territory here, you're getting signals coming in at different times in different places and getting processed at different speeds. This is, by the way, why they use a gun at the Olympics to start the sprinters, because you can get off the blocks faster to a bang than you can to a flash. And that's because your auditory cortex can respond much more quickly to sound than your visual cortex can to vision. And it turns out the weird part is that your brain, even though parts of your brain will process information much faster than others, somehow your consciousness goes through this trouble to synchronize everything. So I stumbled on a paper years ago from the television broadcast engineers in the first days of television who thought, oh geez, we've got a problem. We want to broadcast the audio signals and the visual signals, but how do we make sure that we keep these things synchronized? And they stumbled on something very weird, a discovery they didn't expect, which is that it doesn't actually matter how well they keep it synchronized, because the viewer's brain will synchronize the signals for them. As long as the audio and the visual are within 80 milliseconds of each other, your brain will put those together. They will synchronize them. So for example, if I were dribbling a basketball here, it would look to you like it's synchronized. The sight and the sound of the ball hitting the ground would be synchronized. If I backed up from you and backed up, it would still seem synchronized, until I get to about 110 feet away from you. And then all of a sudden, it would seem asynchronous. You guys have seen this before, right? Where you watch somebody bouncing a basketball and it seems like the sight and the sound aren't matched up. Well, what's special about 110 feet? You can guess the speed of light and the speed of sound are now reaching you at sufficiently different times, about 80 to 100 milliseconds apart from one another. And at that point, your brain can't synchronize it anymore. At that point, your brain sees them as being asynchronous. But the point I want to make is that as long as the signals arrive within a certain window, your brain will go through this trouble of putting them together. So the weird part is, even though parts of your brain are getting information before other parts and processing them faster, it waits for all the information to get there, it stitches it together, it puts together the best story it can about what's happening out there, and it serves that up to you, delayed. So when I do this, I see it and I feel it and I hear it all at the same time. Okay, well, why is this important? Part of why it's important is because causality is one of the most important computations that we do, figuring out what did I make happen in the world and what things just happen. Well, in order to do that, I have to know when I put out a motor act and when I got the feedback. If I do this, but I feel like, oh, I got feedback before I even did the act, I would get the computation of causality incorrect. And it turns out, at bottom, causality is a temporal order judgment, and maybe the most important one that we make. So this led my student and I to start thinking about something a few years ago, which is, okay, well, what would happen then? Well, let me back up for a second. We started thinking, what are the challenges that the brain has in order to make these temporal order judgments? The challenge is, it always takes you about the same amount of time to put out a motor act, but sensory feedback can change. So when you go from the bright sunlight into a dim room, your retina now talks to your brain about 60 milliseconds more slowly. Something called the retinal impulse response function is slowed down when you're in a dim room. So now all of a sudden, I'm doing motor acts, but I'm getting information more slowly. So things would be out of my expectation, out of sync. There's this real challenge that the brain has. It can put out signals, it can get feedback through all these different channels, but it has to know how to align this. And that got me thinking that there must be some way that it's actively keeping that alignment. There must be some way that it's doing this all the time to keep itself calibrated. So here's what we did to test this hypothesis. We have you press a button, and it causes a flash of light. So every time you press the button, it causes a flash of light. But what we do is we inject a little bit of a delay. So you hit the button, and there's about 100 milliseconds before the light happens. And our hypothesis was, look, maybe what the system is doing is it just comes to the table with a single a priori assumption, which is if I'm the one who's clearly causing something, then I should be getting that feedback without delay. And if there's a delay, I should go ahead and adjust my expectations until it feels like there's no delay. So this is our way of testing it. We inject a delay, you're causing it, and we do these ways of measuring where we put people through hundreds of trials, and on every trial we're asking them whether things were before and after, and we actually manipulate these things. I won't go into the details, but what we find is exactly this, that the system recalibrates. We find that very quickly, within about 10 button presses, your brain recalibrates what it thinks is happening in time, so that it now thinks the flash is happening without any delay at all. So surprise number 2 is that time perception recalibrates on the fly all the time, and there's a sub-surprise here too, which is that we realized if we train you up to a particular delay, let's say this 100 milliseconds later, and now we drop a flash in there surprisingly at 40 milliseconds, you're now going to think that this flash happened before you pressed the button. You will say, oh, the flash happened before I even got there, I didn't cause it. So surprise number 2.5 here is this illusory reversal of cause and effect, which we can generate in the laboratory effortlessly. Well, I looked at the way people were having this illusion, where we would suddenly, remove a delay, and they say, oh, I didn't do that. And I thought, gosh, these systems are very sensitive. You have these systems that always need to recalibrate, and people can get these things wrong. Could there be a situation where these systems would break or go wrong, and you would actually have pathologies of time? And what struck me was maybe schizophrenia fundamentally is a disorder of time perception. And I'll tell you why I say that. Because I would watch these subjects in the lab, they'd press the button causing the light, and they'd say, whoa, it wasn't me. I didn't cause that. And I thought that's exactly what schizophrenics do. Schizophrenics have something called credit misattribution, where they'll cause some act, and they'll say, it wasn't me, I wasn't the one who did it. And typically that's followed with some florid story about somebody else causing them to do it. And I thought, God, these normal subjects in my lab seem like that's exactly what they're doing. And then I was thinking about, well, something that's normal that all brains do is you have this internal monologue, right? You generate these internal voices and you listen to them. You have conversations with yourself. That's normal. But imagine now you got the motor and the sensory parts backwards. Well, that's an auditory hallucination. You would have to attribute the voice to somebody else. Because as far as you're concerned, you heard the voice before you generated it. And that would feel like somebody else is doing it. So what we're doing now is testing schizophrenic subjects on these temporal order tests. And we're right in the middle of this now, but our initial data seems very promising. It seems that schizophrenics fundamentally do not recalibrate. They're temporally inflexible, which means that when they're getting feedback from the world that their timing is off, they're not using that appropriately to recalibrate. Now, I can't swear that this is right. Ask me again in 6 months and I'll be able to tell you. But if it's right, it's a real game changer, because it means that if schizophrenia is fundamentally a disorder of time perception, we can have an entirely new way of viewing this and a new approach to rehabilitation instead of just pharmaceutical approaches, which are sloppy and not that effective. We can just have people play video games to recalibrate their timing, and maybe their auditory hallucinations will go away. As I said, this is science fiction today, but ask me again in some months from now. Okay. So that's number 2. Number 3 surprise is I got really interested in this topic a while ago about whether time can run in slow motion when things are really hitting the fan. Because people report this sort of thing all the time. And it happened to me. When I was a child, I fell off of a roof of a house under construction. And it seemed to take a very long time to fall. I felt like I had lots of time to think about things. And afterwards, I was sort of amazed at how long the process seemed to have taken, and I calculated it later, and it was 0.8 of a second. It was all it took to get from top to bottom, so I couldn't understand why that seemed to take so long. So when I grew up and became a neuroscientist, I decided I was going to test this and figure this out. So there are really two hypotheses about why something might seem to take a very long time when you're in a troublesome situation, like your car's going off a cliff or something like that. One is that you've got an increased time resolution. So during the event itself, you've got something like increased time resolution, whatever we would mean by that. And the second hypothesis is that it has something to do with the way that memories get laid down here, or the way that time is experienced here, so that afterwards you look back and you think, wow, that must have taken a very long time. Okay, so what we did to test this is we built a device that we call the Perceptual Chronometer, and it's essentially a wristwatch device that you wear, you strap to your wrist, and it's made of LED arrays that choose random digits, and they alternate between the positive and negative images. And if you see these things alternating like that, you can very easily read, oh, that's the number 4. But if we speed it up just a little bit more, past a very sharp threshold, then you can't read the digit. It just looks like a flat field of LEDs, right? Because the positive and negative are alternating too fast, and they blend together. Okay, so we make this into a watch. We strap it to people's wrists. There's a chip inside that chooses random digits, and it flashes these digits at you and can flash them at different speeds. So we can find out what is the speed at which people can identify the randomly chosen digits, and then and then can we make it faster than that so that they can't read the digits? And can we use this as a way of measuring how fast people are seeing the world? The idea is, let's say we speed it up so you can't see it, and now we put you in a really scary situation where you claim you can see the world in slow motion. The question is, can you tell us what the digits are or not? Okay, so we built the device, but then the question was, all right, how do we make people really scared? Okay, so of course the first idea we had was stick volunteer subjects in a life-threatening, terrifying situation. But we're scientists, so we always try to come up with a better idea. We never actually did come up with a better idea, so we went with the first idea. And what we did is we dropped people from a 150-foot tall tower in free fall, and we had this strapped to their wrist. And what we were asking was, while you're falling to your death, presumably, can you read what's on the wristwatch? Okay, so there were two parts to this experiment. One was, we had people, so before I tell you the results of that, we had also people take a stopwatch and watch somebody else fall, and then retrospectively estimate how long the other person's fall was. So this is them estimating someone else's fall. And then we had them, after their own fall, take the stopwatch and recreate how long their own fall took. And what we found, not surprisingly, was there was about a 36% duration distortion. People thought it took much longer when they were remembering their own fall. It's actually probably much worse than this. It's just that people would say, okay, well, I'm going to stop the watch because I'm kind of embarrassed that I'm still going. But it felt like a really long time. So it's at least 36% duration distortion in terms of how long it felt. But the question is, could they actually read in slow motion like Neo in The Matrix? So I'm going to skip some of the details, but I'm just going to say, we're asking about the accurate digit identification. Here was the expected performance based on time slowing down by 36%. And what we find is that there's no difference in the in-flight performance or just ground-based control, meaning people are not actually seeing in slow motion. So here's this weird thing, that they feel like it lasted a really long time, and anyone who's been in an accident like this knows this feeling that it took a really long time, but they're not actually seeing in slow motion. So this, for me, was surprise number 3, which is that time is not one thing. You can have a distorted duration, but that doesn't entail the other consequences you might imagine. It's not like you're taking a movie and slowing it down. And in fact, if you ask somebody who's been in one of these car accidents where they said, oh my God, it took forever, the glass flying, just ask them, say, okay, well, the person next to you who was screaming, did they actually sound like they were saying, no? And the answer is they did not sound like that, because time is not a single thing that gets stretched out like a movie. Instead, time is fractionated. You have different parts of your brain that care about duration, and you can warp those. You have other parts of the brain that care about simultaneity judgments, other parts that care about flicker rate, other parts that care about temporal order judgments. And these are all separable. And it turns out that in your brain, these normally work in concert. So you think that time is this beautifully unified thing. But what we can do in laboratory situations is start teasing these things apart and show that actually duration can get warped totally independently of the other consequences you might think that might entail. So the last thing I'll show you is a way that we were able to address this a little more finely in the laboratory with a slightly more sober experiment, which is using something called the oddball effect. It happens that if you're looking at a series of things and then there's something unusual, the unusual thing seems to last longer. So if you're judging the duration of these, did you guys see how the clock seems to last longer there? So they're all presented for exactly the same duration, but it turns out that an oddball in a visually presented stream like this seems to sort of be expanded in its duration. Okay, well, why is that? Well, one thing we found is also, I should just mention, it's not just the oddball, but it's actually the first one in the series also seems longer than the successive ones. So if I were just to make a cartoon of this, here's the series, and here's some oddball that I'm throwing in. And if we plot the perceived duration, what you find is that the first one in a segment seems to last longer, and then the oddball seems to last longer also. Okay, well, it turns out that you might notice I didn't label the units on the y-axis here because you could think about this as an expansion in time of the oddball or first one, or you might think of it as a contraction of the thing that's being repeated. Maybe it's that the thing that's being repeated is contracting in its perceived duration. And the reason that's an important distinction is because when I started thinking about it that way, I realized that actually that maps onto something quite interesting, something called repetition suppression, which simply means when you show the same thing to the brain over and over, you have a diminishing neural response. So the first time I show you the shoe, your brain goes brrr, and the second time I show you the shoe, your brain goes brrr, and then the third time it goes brrr. Your brain doesn't care as much. Now, this used to be interpreted as fatigue of the neural response, but probably the better interpretation is that it has to do with coding efficiency. Your brain says, oh, I get it, it's going to be a shoe, it's going to be a shoe. And as your brain gets better coding efficiency, it can burn less energy. Energy, as Malcolm was saying in his talk, is one of the most important things that goes on in the brain. We are mobile creatures that run on batteries, and it is the most important thing for us to conserve. And so smart brains are always trying to figure out how can I predict what's going on so that I use less energy. So the point I want to make here is that when you look at what happens in the physiology with the neural response, it happens to map on exactly with perceived duration. I can use either axis here, and what you see is the same pattern. Here's just an example of this, one of 1,000 examples on repetition suppression, which is, if you're showing a monkey the same thing over and over, the red dots are where you're showing the same stimulus over and over, and you're looking at the response of the neuron in spikes per second. You see, there's a diminishing neural response each time you present it. And so the suggestion that we recently made is this really weird relationship between what's happening with neural response and subjective duration. It's like they're mapped onto each other. So in other words, the suggestion that I recently made in the literature is that subjective duration is somehow indexing the amount of energy used in the brain. Now this sounds crazy, right? I mean, how could this be? I don't know how this could be. It just seems to map every single thing that we've been able to test and measure and find in the literature. So I'll just give you an example of this. It's not just changing the size of the neural response by causing something by, repetition suppression. It turns out you can change the neural response in lots of ways. You can make things bigger or brighter or moving. You can change neural response in lots of ways. And we started going through the literature, and we found this scattered confederacy of duration distortions in the literature. And what we find is that if you make something brighter, for example, that causes it seems to last longer on the screen. So if I show you a dim square and then a bright square, it'll seem like the bright one lasted a longer time. Same if I show you a bigger square. Same if I show you more numerous things rather than fewer things, it seems to last longer. If I show you something moving rather than static, it seems to last longer. If I show you something looming rather than contracting, it seems to last longer. And so on. There's lots of things that we discovered in the literature. These are all different ways that you can distort duration, and they all have the exact same thing in common. They all fall exactly under this framework, which is if you cause the brain to burn more energy, it will seem to have lasted longer. Now, this is completely crazy, except that it happens to be consistent with everything we can find and everything that we're studying in the lab. So surprise number 4 then is that the suggestion I'm making is that subjective duration varies with neural energy. Now, I don't know that it's proportional. It might be nonlinear, and there are 150 ways that this needs to be refined. We don't know if it's for particular cell types in the brain, particular brain areas, particular types of patterns of activity. Don't know. All I know is that this seems to be true right now, that these things map onto one another. So just to summarize the 4 surprises that I told you, the first one is that we live in the past, and if information slightly in the future of an event can influence what you think you see at the time of the event. Temporal order recalibrates dynamically, and it only takes several seconds for you in the laboratory to start readjusting your timing such that we can cause an illusory reversal of action and effect by suddenly removing the delay, and then you think something happened before you even did it. It's trivial for us to do that in the lab. Time is not one thing, because we can find lots of situations where, let's say, we make you believe that a duration was much longer or shorter, and that doesn't change the other things you think might be entailed by that. And finally, this very wacky hypothesis that just seems to map with all the data right now, which is that subjective duration, how long you feel something lasted, seems to be an index of how much your brain had to work to represent that object. If you present something in the brain, brrr, it'll seem to have lasted a long time. If you present something else, pop, 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 it seems to have lasted a shorter time. And what this all leads us to then, finally, is this question of what is t in the equations. All of our physical equations always get built on top of our intuitions. And what I want to emphasize here is that when we think about time, it's pushed through these psychological filters, these very stubborn, deep psychological filters, and it's only very recently that my colleagues and I have started really teasing this apart and trying to figure out what is time to the brain. So thanks very much, and I'll take questions.